Hello, I Anand Jain from Hanumangarh, Rajasthan welcomes you to your favorite Shridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering subjects. Today in our playlist Basic Electrical Engineering and Class 12th Physics, in our chapter Alternating Current Circuit, we'll learn behavior of resistance inductor series circuit in alternating current supply, and will understand the concept of impedance which oppose flow of alternating current in RL series circuit. And in RL series circuit, current lags voltage by a phase angle in between 0 and 90 degree, and the value of phase difference angle depend upon the ratio of inductive reactance and resistance. So let's understand RL series circuit, the concept of impedance, and calculation of phase difference. A pure resistance of value R ohm and a coil of pure inductance L Henry connected in series to a alternating voltage source, and this is called RL series circuit in alternating supply. Now, application of sinusoidal alternating voltage across this RL series circuit produce alternating current of same frequency but with a phase difference, and current lags voltage by a certain phase angle phi. In a series circuit where R and L are connected, the same amount of current flows through them, and let's take that current as standard reference sinusoidal current with phase angle 0 or T0 instantaneous value 0 as Im sin omega t, and this same current is current of resistance and current of inductor. In this series combination of resistance and inductor, total instantaneous voltage applied across series combination small v is sum of instantaneous voltage across resistance and inductor, and resistance voltage is proportional to current flowing through the circuit is equal to IR, and since the same current is flowing through series inductor and inductor voltage is proportional to rate of change of current with respect to time, and it is L di by dt. If we assume current in this series circuit as standard reference sinusoidal current I equal to Im sin omega t having T0 instantaneous magnitude 0, then voltage across resistance is in phase with current and is Im into R sin omega t, and voltage of inductor, if we calculate that by differentiation of this current function, then differentiation of sin omega t will become omega cos omega t, omega with this L become omega L, and we'll get voltage of inductor leading current by 90 degree as Im omega L cos omega t, and total instantaneous voltage is instantaneous voltage of resistance and instantaneous voltage of inductor. Now IMR product for mathematical simplification assumed as C cos phi and Im omega L assumed as C sin phi, then this expression will become C sin omega t plus phi, where C is square root of IMR and Im omega L given by this expression, and if we brought Im common, and this square root of R square plus X square is given a new name known as impedance Z, and this impedance Z perform the same function as R is performing in pure resistance or omega L is performing in pure inductor. And in this RL series combination where we have both resistance and inductive reactance, their Pythagoras calculation become impedance. It is that property of RL series circuit which oppose flow of alternating current through it and demand proportional voltage, and this is now relation between peak magnitude of voltage Im/Z, that is proportional to Im and proportionally constant is Z, and the phase difference angle between current and voltage by which voltage leads current is given by this expression. Division of Im omega L with IMR gives us tan phi, or tan phi is equal to omega L by R. So phase difference angle depends upon circuit resistance, inductance and supply frequency, or it is as per ratio of inductive reactance and resistance, and if the two are equal, tan phi is 1 and this phase difference angle become 45 degree, and if XL is more than R, this angle will become more than 45, otherwise it is less than 45. The previous trigonometry identity methodology to find out relation between peak current and peak voltage and to find out phase difference between current and voltage, this phi, is quite tedious and time consuming, and it can be applied only when there is only two element in a series. For more than two, this method become again very cumbersome. A better systematic and convenient approach is given by C.P. Steinmetz, and that is Phasor representation approach. and if Vm is divided by root 2, that become RMS voltage across this RL combination. Similarly, RMS voltage across resistance is VR and RMS voltage across inductor is VL. Then we can relate VR, VL, V and current of circuit as rotating vector of same frequency or in the same direction, and when that rotation is frozen at any instant, or say at instant when current phasor is at horizontal reference, rotating phasors become simply vector, and simple vector analysis will fetch a convenient relation between RMS voltage, RMS current and phase difference angle between voltage and current. To find out complete phasor diagram of RL series circuit, we'll first find out relation between circuit current and voltage of resistance, then we'll find relation between circuit current and inductor voltage, and then sum of resistance and inductor voltage will give us total voltage, and by that we'll get magnitude relation between RMS current, RMS voltage and phase difference angle between supply voltage across RL series circuit and current flowing through RL series circuit. Since in a series circuit current is the same through resistance R and inductor L, so we can take this current as common. All sinusoidal alternating quantities, current through RL circuit, voltage across resistance, are represented by rotating vector or phasor, and current rotate in anti-clockwise direction with angular velocity equal to angular frequency. And for study analysis, the rotation of current phasor is frozen when it is at horizontal reference line, and resistance parameter is also placed at horizontal reference line. So voltage across resistance come along resistance line or at horizontal reference when current is at horizontal reference, and we got current and voltage are in the same phase as illustrated in wave diagram also, and the RMS voltage of resistance is equal to RMS current multiplied by resistance in ohm, and it is in phase with current. The sinusoidal time alteration of alternating current in series RL circuit shown by orange wave shape and voltage across resistance shown by cyan wave shape clearly indicate that identical phase condition of current and voltage of resistance come at the same instant, and this is also illustrated by this phasor diagram where current and voltage of resistance are in phase. At t equal to 0, the projection of current and voltage of resistance both indicate 0 instantaneous value, and with rotation of phasors and passage of time, both instantaneous value of current and voltage increases. They attain their respective peak after quarter cycle operation, and then the values decreases, attain 0 instantaneous value once again, and now the polarity of voltage and direction of current has changed, attain negative peak, and one complete rotation of phasors generate one complete cycle of this variation. So this wave diagram is replicated in this phasor diagram where series circuit current and voltage of resistance are in phase with each other. In this series RL circuit, the same current of resistance also passes through inductor, and we know that in a pure inductor, voltage across inductor leads current through inductor by 90 degree as shown in these wave diagram. The orange wave represent current and cyan wave represent voltage, and peak of voltage come before peak of current with a phase difference of 90 degree as shown here, and we know voltage across inductor is omega L times current. So RMS voltage across inductor and RMS current of inductor are related as VL is equal to I omega L, and this product angular frequency and inductance in Henry is known as inductive reactance or XL, that represent property of pure inductor to oppose flow of alternating current through it and demand proportional voltage for current flow without consumption of energy. Now to explain the same wave diagram by phasor relation, series RLC circuit common current phasor rotation is frozen when it is at horizontal reference line, and we know pure inductor is represented as 0 plus JXL. It is on vertical positions, or it is XL angle 90, so its position is here. So voltage of inductor come across that XL line, and this phasor diagram clearly indicates that voltage of inductor leads current by 90 degree. In a pure inductor, RMS voltage across inductor is equal to RMS current multiplied by inductive reactance, and voltage phasor leads current phasor by 90 degree. And this phasor representation of voltage phasor and current phasor represent this sinusoidal time varying alteration of voltage and current. At T0 condition, current got 0 projection on vertical axis, so its instantaneous magnitude is 0, and voltage got full peak projection on vertical axis, so voltage across inductor is instantaneously at peak value at t equal to 0. And as time passes, phasor rotates and instantaneous value of current through inductor increases and voltage across inductor decreases, and after a quarter cycle time interval, phasor rotates by 90 degree and instantaneous value of voltage decreases to 0 and instantaneous current increases to positive peak as respective projection on vertical axis indicates the same. Further rotation of phasors change polarity of voltage across inductor and reduce current magnitude through inductor, and one complete cyclic rotation will produce one cyclic variation of current and voltage in pure inductor, where voltage leads current by 90 degree. So this wave diagram and this phasor diagram represent the same thing. To find out relation between current of RL series circuit and voltage applied across this series combination, we have to draw a complete phasor diagram and let V is RMS value of voltage applied across RL series combination, I is RMS current passing through RL series circuit, and VR is RMS voltage across resistance, and VL is RMS voltage across inductor. And when rotating current phasor is taken at horizontal reference, the voltage of resistance equal to RMS current multiplied by resistance comes in phase with current as shown by this phasor diagram or VR position. Similarly, voltage of inductor leads current by 90 degree and its RMS magnitude is equal to RMS current multiplied by inductive reactance. As per Kirchhoff's voltage law, the sum of voltage across this series combination of resistance and inductor or total applied voltage is phasor summation of voltage of resistance and voltage of inductor. V is equal to VR plus VL, and when the rotation of all rotating vector or phasor is frozen with current at horizontal reference, the position of VR along horizontal line, along R line, and voltage of inductor along XL line are as shown. And now these rotating vector or phasor are just like simple vectors, and we take tel of VL on head of VR and connect tel of VR and head of VL as sum of VR plus VL, and this is total supply voltage. So we can say in this right angle triangle, total supply voltage is Pythagoras combination of base voltage VR and perpendicular voltage VL as given by this Pythagoras relation. So in this right angle triangle, Pythagoras relation relate voltage of resistance, voltage of inductor, and total applied voltage. Voltage of cross resistance is proportional to current flowing through resistance, and V is IR. Similarly, inductive reactance oppose flow of current in inductor and demand voltage across it, and VL is IXL. And in this Pythagoras relation, in place of VR IR and in place of VL IXL is substituted. Now this I come as a common parameter, and this becomes square root of resistance square added to inductive reactance square, and this square root of R square plus XL square is given a new name known as impedance Z, where Z is square root of R square plus XL square. Now this Z represent total opposition offered to the flow of alternating sinusoidal current through series RL circuit, and this opposition demand proportional voltage for flow of alternating current in RL series circuit, and it is just like resistance or inductive reactance is measured in ohm, and it is not simple sum of R and XL, but it is by phasor summation become a Pythagoras calculation. So for RL series circuit in alternating supply, the total opposition offered to current flow is called as impedance Z, and impedance square is equal to resistance square plus inductive reactance square, or impedance become square root of R square plus XL square. And it's not a simple summation, but it is a Pythagoras calculation, and two example will illustrate this conveniently. If circuit resistance is 30 ohm and inductive reactance is 40 ohm, so it is 30, it is 40, then their sum is not 70. This Pythagoras summation is obtained by hypotenuse as square root of base square plus perpendicular square, and it is 30 square plus 40 square. 30 square is 900, 40 square is 1600, total is 2500, and square root will fetch 50 ohm as value of impedance for R 30 ohm, XL 40 ohm. Similarly, if R is 12 ohm and XL is 5 ohm, then Pythagoras calculation of R and XL to give Z is given as Z is square root of R square 12 square and XL square 5 square. 12 square is 144, 5 square is 25. It is 169 square rooted give us 13 ohm. So it is 5, 12, 13 combination. Earlier was 3, 4, 5 combination which fetch for 30, 40 impedance 50 ohm. Similarly, if both R and XL are equal 1 and 1, then impedance will become root 2 times, and if R and XL got 1 and root 3 ratio, then impedance will become 2 unit. The complete phasor diagram or current or voltage relationship can be obtained by study of impedance triangle, and for impedance triangle we know that R got no imaginary part, it is entirely on horizontal line, it is R angle 0 or R plus J 0. Similarly, inductive reactance won't have any real part, it is plus J type quantity, or it is XL e raised to power J90 on positive vertical line. So this is position of R vector, this is position of XL vector, and their summation is Z vector. And it is very interesting, when rotating current phasor is stopped at horizontal reference line, voltage of resistance come along resistance line, voltage of inductor come along inductor line, and the total voltage of this circuit of series resistance and inductive reactance having total opposition indicated by impedance Z come across impedance line, and resistance, inductive reactance and impedance triangle proportionally become voltage phasor diagram of VR, VL and total voltage. So the angle between supply voltage and circuit current is the same as angle of impedance and resistance, and tan of this angle, tan phi, is perpendicular upon base, it is VL upon VR or XL upon R or omega L over R. So this will give us angle phi. So we can say if this current is at horizontal reference given by standard reference sinusoidal expression I equal to Im sin omega t, then its voltage lead current by phi angle, and its instantaneous magnitude is given as Vm sin omega t plus phi, where Vm is Im times Z. So we can say in a RL series circuit, voltage leads or is in anti-clockwise direction and current lags as it is in clockwise direction from voltage phasor. If we consider this voltage phasor as a reference phasor, then we'll say current lag voltage by an angle phi, and voltage and current will be expressed in trigonometric expression like this. Practice of this numerical problem will enhance our confidence level. We have given a RL series circuit connected to AC supply. The resistance value is 150 ohm and inductive reactance of this circuit is 100 ohm. In place of ohmic value of inductive reactance, if one has given us L in Henry and omega in radian per second, then the product of omega and L will give us value of inductive reactance in ohm. Now we have to calculate for this circuit having resistance 150 ohm and inductive reactance 100 ohm, impedance in ohm, current in ampere, and the phase angle between current and voltage when our 200 volt sinusoidal voltage is applied. So we know that in a RL series circuit, impedance is Pythagoras calculation of resistance and inductive reactance, and it comes as square root of resistance square, resistance is given 150 ohm, and inductive reactance square sum, and this sum is after squaring of the two quantity comes as 32,500, and when square root is taken it comes as 180.28. So impedance of this circuit is 180.28. Once we got impedance, we can apply V and I relation, which is for pure R V is equal to IR, and for pure inductive reactance it was V is equal to IXL, but for RL series circuit it is V is equal to IZ or I is V by Z. V is given 200 volt, this is RMS value, and Z is 180.28. So RMS current in RL series circuit is 1.11 ampere. We can also find out phase angle between current and voltage as tan phi is XL over R, XL is 100 ohm, R is 150, and if we take tan inverse of that, it gives us angle between current and voltage, and current lags voltage by 33.7 degree. We can also find out voltage of resistance as IR, and it is 166.5 volt, and similarly voltage across inductor is IXL and XL is 100 ohm, current is 1.11 ampere, so it is 111 volt, and the phasor summation of 111 and 160.5 comes as 200 volt. This beautiful small learning video has explained behavior of resistance inductor series circuit in sinusoidal alternating voltage supply, and now you understand the concept of impedance and impedance triangle, and the same impedance triangle become voltage phasor diagram, and angle between impedance and resistance become angle between supply voltage and circuit current, and since impedance is clockwise to resistance, XL is plus J type, voltage leads current or current lags voltage. Our other learning video of the same playlist are equally useful to improve your subject understanding and exam score. And if you need online doubt clearing classes or exam centric notes from our channel, do join our membership. Happy learning. Have a nice time. Thank you very much.